Yeah. So I'm going to talk to you a little bit about quantum programming with PennyLane for quantum chemistry. Um, I will assume that most of you are familiar with at least the basics of quantum computing and a little bit of quantum chemistry, but I'll try to keep it at a good level. Part of this presentation is going to involve a little bit of hands-on coding. So once we get to that point, I'll let you know, and it'll be follow-along coding exercises for an example of the variational quantum eigensolver in quantum chemistry. So if you're not familiar with Xanadu, the company that I work for, we are a quantum computing company based in Toronto, Canada, with the mission to build quantum computers that are useful and available to people everywhere. We were founded about 8 years ago in 2016. We continue to be headquartered in Toronto, in Canada, and we've grown very quickly over the past 8 years. We recently surpassed 200 people in the company. And everything that we do at Xanadu is very much driven by this mission. So we're both a hardware and a software company. We're building the quantum computers, but through PennyLane, we also want to make them available and useful to people everywhere. So quantum computing is often motivated by this quote by Richard Feynman, who pointed out that ultimately nature is not classical. So one shouldn't expect to be able to get an accurate simulation of nature by using classical computers. If you really want to get into certain details, especially of quantum mechanical systems, you ultimately need an analog to that quantum system, which would be a quantum mechanical computer. Now, if you want to venture some ideas as to why that is, why is this such an important observation? If you can put on the chat why quantum mechanics poses certain limits to what we can simulate, or rather the quantum mechanical nature of things poses limits. So ultimately, if you're still thinking about it, the reason why is that especially for quantum systems, the scale of certain problems simply becomes too large for the problem to be handled efficiently by classical computers. And I highlight here the word certain and efficient because it's not, quantum computers won't be able to solve every problem that a classical computer can solve. And quantum computers won't be able to solve problems that in principle, if given, let's say, an infinite amount of time or thousands of millions of years, that a classic computer wouldn't be able to do. So it's really looking to accelerate the time scale to be able to solve certain problems. So with that, since quantum chemistry involves by its nature quantum mechanical systems, so molecules and materials, it seems like a perfect ground for testing a lot of the ideas behind quantum computing. The ultimate goal of quantum chemistry is ultimately to be able to computationally predict large-scale properties of systems, of matter, of collections of molecules, up to the smallest scale. So really getting to the details of the molecular physics of a material. And there's countless applications to this. There's it's not necessarily that quantum computing will be useful for these, but you can think of, designing better drug molecules, assisting in those things, assisting in developing new materials for better materials for things that exist already. So better conductors, better insulators, better batteries is one thing that we're focused in a lot at Xanadu. So really the applications would be countless in terms of what you could do with simulations on a quantum computer. So most of you are probably familiar with this picture of atoms on the top left, where it's a popular cartoon of what atoms and molecules look like. Is electrons orbiting a nucleus about set orbitals, very much like the planetary system. In reality, that's not really true. Molecules and atoms are really best thought of as kind of clouds, hazy clouds of probability, where the electrons and the nuclei don't necessarily follow a certain path, but they exist in this kind of cloudy cloud of probability. So in order to be able to compute things about these systems, you need something compatible with that picture, things that can model these probabilistic clouds using math and software. Something happened here. Yep. So, as I said before, the goal of quantum chemistry is really to understand the collection of atoms and molecules that make up materials. In principle, when quantum mechanics was founded almost 100 years ago, the problem was in some sense solved. So all collections of molecules, all materials that exist, in principle, are described by a Hamiltonian. So we can think of it as a matrix to some extent. And the equation governing the behavior of molecules is this one given here, the Schrödinger equation. So that in principle, if you're able to solve this equation, you can compute any property you want about a given molecular system. Of course, we've discovered since then that in practice, for molecules beyond 2 or 3 electrons, this is very difficult to solve. And for cases of materials and more complicated collections of molecules, it's virtually impossible to solve, even computationally. So ultimately, one of the main applications, or one of the main topics in quantum chemistry, is estimating the ground state energy of a collection of molecules, or of a molecule itself. The reason for that is because ground state energies are sort of the doorway to estimating other more important properties of molecules. You can think of things like polarizability, so how a given material will react to an electric field or light. You can compute reaction rates or reaction pathways and try to design better catalysts or different catalysts. Really have a certain amount of control over chemistry that is very difficult to have in experimental settings. You can predict things like band gap energy, so the difference between a ground state and an excited state, which is important, for example, for optical properties of materials. The workhorse method for this kind of problem is known as the variational method. If you've taken any quantum mechanics course, you've probably heard of this method. The principle is fairly simple. It says that if someone were to give you a complete description of the ground state of a molecule or of a system, which I denote here by this psi 0, if you calculate the average value of the Hamiltonian, you get the ground state energy that you're after. What that means then is if you guess literally any other wave function, any other description of the state, you will get a different estimate for the ground state energy, which I've denoted here as E alpha, E subscript alpha. And the variational method rests on the guarantee that no matter what function you guess for the ground state, as long as it's not the true ground state function, you're guaranteed that your estimate for the energy will always be larger than the true ground state. So you're guaranteed that no matter what number you guess, the ground state energy is somewhere below that. So in principle, all you need to do for this variational method is to guess a good description of the ground state, a good psi alpha, and then minimize this average value, this expectation value of the Hamiltonian. Typically, alpha is a set of parameters that you vary, that you optimize given some criterion, so as to lower that value as much as possible. So the way I described it to you, this seems like it's an easy problem. You guess you have some educated guess for the description of the ground state of your system, and then you just calculate this average value and minimize the parameters. So what do you think is the difficulty here? Why haven't we been able to apply this to systems why is there a need for quantum computing, basically? Or why is there a need for complicated methods in computational chemistry? You can unmute yourselves, you can post on the chat. Yeah, exactly. So there's two problems. One of them is guessing a good ansatz, which is this psi alpha is difficult in practice. You can make educated guesses, but really when you get to large molecules, it becomes really complicated to make even an educated guess. And the other one is system size. I mentioned that one of the problems that quantum computers hope to address is the scale of problems. When you get to molecules beyond even 20 electrons, it becomes very difficult to apply classical computational methods to it. So even if someone were to magically give you the true ground state function, even calculating this expectation value will be computationally very difficult. So I would say the solution, or one of the proposed solutions to this problem, is something known as the Hartree-Fock method. This was a method that was developed shortly after quantum mechanics was developed, so almost 100 years ago as well. I'd say more like 90 years. The idea is to address the problem that comes from the size of the system. You typically have to take into account how every electron in an atom or a molecule interacts with every other electron. You have to think of all of the possible combinations in which electrons can interact with one another. The Hartree-Fock method says instead of doing that, we're going to approximate a solution to the Schrodinger equation by taking what's known as a mean field approach. So rather than treating each electron or all of the electrons together at the same time, you treat each electron as an independent particle, and you describe all of the other electrons as a cloud of electric charge, essentially, that is interacting with your one electron. You do this with every single one of them, so that you kind of average out the interactions, and you remove any type of correlation between individual electrons in this way. This is really the true workhorse of quantum chemistry. It's based on the variational method, and it's really the starting point for any computational technique in chemistry that is concerned with estimating the ground state energy of a system. So the Hartree-Fock method gives you a set of equations that you can solve. They're not easy to solve. You have to solve them what's known as a self-consistent way. So whatever solution you get for one of your electrons, the other solutions from the other electrons have to be consistent with that one. So it's still a fairly complicated problem. It's a non-linear optimization problem that is still difficult to solve. But what you get out of it once you're able to solve it is an approximate description of your ansatz. So you get a better approximation of an ansatz as a function of what's known as molecular orbitals. So what are molecular orbitals? If you're dealing with just simple atoms, so think something like helium or lithium atoms, the way that we describe them, so the way you move beyond a hydrogen atom, is you describe the wave functions as a combination of other functions. Typically, you would think that something like a combination of different wave functions that would describe the hydrogen atom, which is just a single electron with a proton, and you superimpose that, would work well. In principle, that doesn't work too well. There's other functions that work better. one commonly used function is a linear combination of Gaussians. This is purely for computational efficiency. It makes the solution of the Hartree-Fock equations a lot easier. And it's not such a bad description of the true wave function, even if it's known not to be exact. When you superimpose different Gaussians, you can actually get fairly precise descriptions of the atomic orbitals. These parameters, this AI and alpha I, these are parameters that you would vary in a way to optimize the description of a given atom. So these are pre-optimized parameters for a given atom. And it really gives you a fairly complete description of how the electrons are configured, how the atom is configured. And these are known, this is an example, these Gaussians are an example of a basis set. In practice, you have other possible choices of basis sets, but the Gaussian one is really the most commonly used one. So if in the case of atoms, you have this linear combination of Gaussians or linear combination of, for atomic orbitals. When you start dealing with molecules, molecules are, of course, collections of atoms. So the way you would describe it is from the atomic orbitals, you would superimpose them, depending on what atoms constitute your given molecule, into a linear combination of atomic orbitals. Now you get an approximate description of the molecule by describing in some detail, in some preconfigured detail, each of the atoms that compose that molecule. So what the Hartree-Fock method is, it falls under something called wave function methods in computational chemistry. That means that you're trying to build up a good approximation for your wave function. The Hamiltonian its form is well known, even if it's complicated to, it becomes very complicated. What wave function methods do is they focus on getting a good description of this psi by constructing, as I said before, a basis set for defining atomic orbitals, using those to construct a good description for your molecular orbitals out of a linear combination of the atomic ones. And then ultimately even superimposing the molecular orbitals to build up your complete wave function with certain parameters that you can tune and optimize to improve that description. You can imagine that when you get to very many electrons, this becomes very complicated. It becomes a many-body wave function, which is known to be extremely complicated for complex molecules. And one of the things that a method like the Hartree-Fock method ignores by taking this mean field approximation approach is, as I mentioned earlier, correlations between electrons. So one of the main limitations of the Hartree-Fock method, even though it's still a fairly complicated problem to solve, is because it ignores these correlations, it will ultimately give you a limited description of the molecule. What that means in practice is any estimates of the energy that come out of the Hartree-Fock method eventually hit a hard limit known as the Hartree-Fock limit, where no matter how else you change your optimization method, you're not going to get a better description of the energy. This graph here that I'm showing you is an example of that. So the dots demonstrate the exact values. You can think of them for this purpose as experimental values of the energy of the hydrogen molecule at different distances. So you take the hydrogen, each hydrogen atom, you put it at different distances, you measure the energy, and you save that, and you build up a graph out of it. The black dots again are the experimental values. The solid line is your Hartree-Fock approximation. And you can see that it eventually you start overestimating the true energy with Hartree fog. And it doesn't matter what you do, because you've ignored these correlations, you're not going to be able to do any better than that. That being said, even though the Hartree fog method hits this hard limit with the energy, it still gives you a good description of the wave function. So it still gives you a good basis of molecular orbitals to be able to approximate this wave function. And that's why it's still the every quantum chemistry computation begins essentially with the Hartree fog method to get at least this nice description of the molecular orbitals. If you're familiar with quantum mechanics, you've ever done quantum mechanics in practice, you know that the Hamiltonian is typically described in a given basis set. So you choose a certain description for your system, you need to express the Hamiltonian in that same description. It's a little bit like choosing a coordinate system in a problem. If you're describing your system in a given coordinate system, you also need to describe the Hamiltonian in that coordinate system. You would think, because the Hartree fog method has this limitation, that the Hamiltonian would also suffer from similar problems, but it turns out that if you express that in the same Hartree fog basis, the Hamiltonian is effectively very accurate, or as accurate as you need it to be for most intents and purposes. So again, the quantity that you get out from the Hartree fog method is not so much a good estimate for the energy, but it's more a good description of the wave function that you can build up on in what are known as post-Hartree fog methods. If you have any questions, by the way, feel free to put them on the chat or interrupt me. I'm happy to take questions as they come. Okay. So over the last, I'd say 90 years, the quantum chemistry community has developed a whole range of different methods. This slide is a little busy. The main thing to take away from this slide is if you want to improve the description of your system, you're gonna have to pay a little bit more for you're gonna have an increased cost in computational time and computational efficiency. So there's no free lunch. If you want a better description of something, you're gonna have to pay for that. And that's what this graph is essentially showing. So the Hartree fog method is highlighted here in red. You're very limited in describing the full electron correlation because you're using a limited basis set in the atomic orbitals, in the molecular orbitals. There's been a variety of other methods developed, things like the couple cluster, full configuration interaction, all that. They will give you a better description of the correlation between electrons in complex molecules, but you pay for that by having to use a bigger and bigger or more detailed description of your system. And what that means ultimately is you increase your accuracy, but you're also going to need to pay for that and increase CPU time. And CPU time is something that's very expensive. It's not something that runs in a few seconds on your laptop, which is what, when you solve simple problems, what you're used to. This is really talking about computations that can take days or weeks in a supercomputer. So it can become very expensive and simply not practical to do in certain cases. So this is really where quantum computers start to come in. We have this need for more precise computations in certain applications, but we don't have the means, or we don't have the resources to invest in those computations. So the hope of quantum computers is that they'll be able to improve on the Hartree fog approximation in ways that scale better than all of the other methods that have been developed. So they will still be able to give us that better accuracy that we get from other methods, but it won't cost us as much in terms of compute time or in terms of resources that we have to put into it. Just as the other ones are known as post-Hartree fog methods, methods developed for quantum computers, so quantum algorithms for quantum chemistry, are known as quantum post-Hartree-Fock methods. The reason they're called that is because just as the classical methods, they start off with a Hartree-Fock computation. So the Hartree-Fock method will give you an idea of where you should start with your problem, and then the quantum computer will hopefully be able to adjust your ansatz or the guess for your wave function in a more computationally efficient way than the other classical methods. And then you can go back to the variational method and calculate expectation values or average values of your energy. Okay, and this is the example that we're going to see doesn't show that advantage necessarily. It was a very early idea developed about 10 years ago, about a decade ago, with the limitation on the resources that existed at the time in terms of number of qubits that could be had on real quantum computers. So that some of you have probably heard of this method. It's the variational quantum eigensolver algorithm. It's an algorithm that it comes out almost directly from the variational method. So I told you that the variational method is really the workhorse of quantum chemistry, and that extends to this algorithm. It's a way of trying to estimate the ground state energy by first preparing the Hartree-Fock state. So again, you start off with a classical computation to guide you a little bit in your problem. On the quantum computer then creates or improves on that ansatz, on the ansatz that comes out of the Hartree-Fock state. That's what we're going to call the post-Hartree-Fock states. So it's hopefully a better description of the ground state. You're going to measure again the expectation value for Hamiltonian, so the expectation value of your ground state energy. And then classically, on a classical computer, you would optimize the parameters in the circuit, so the parameters that develop that better ansatz, that post-Hartree-Fock state, to further minimize the expectation value of the energy. So the VQE algorithm is what's known as a hybrid algorithm, where part of the computation is done by the quantum computer, the part that the quantum computer is good at with the limited resources that exist. To some extent now, we still have a limited number of qubits. They're not protected from error, so we can't do very many computations. And then the more computationally expensive part, or the part that the classical computer is really good at, which is the optimization of the parameters, that is done with a classical computer. And the two talk to one another through this iteration of optimization of parameters. All right, so let me just pause here for a moment. Are there any questions so far about the main setup, the motivation for this? If I'm going too quick, just let me know. I can slow down a little bit. We'll get pretty soon to the hands-on part. So you'll be able to try out a few things with PennyLane, which I hope will be interesting for you if you've never tried it, especially. Okay, so the variational quantum eigensolver is part of a family of circuits or computational models in quantum computing known as variational circuits, which are a subset of the bigger field of quantum machine learning. So these are parameters that have, I guess, models that are described by circuits with parameters that can vary. It's very much like machine learning in that sense. You have a certain task you want to accomplish, a certain goal you want to describe, or a model that you want to have your circuit learn to some extent. So naturally, more generally, quantum machine learning models can be used to do the same things that machine learning models can do. So things like classify data points, regression analysis, describe, get better descriptions of something out of a set of data points. The algorithm is, again, familiar to those of you that have done machine learning. You construct a cost function that describes the goal that you want to achieve. And you want to minimize that cost function by varying these parameters as much as possible. This is a whole field that has been developed, especially over the last 10 years. And is probably one of the main reasons why this variational circus is variational quantum eigensolver was developed. So the ingredients that we're going to see in the VQE are the similar ingredients to what you see in just about any variational algorithm. You're going to have a circuit ansatz. This is just a fancy way of saying a guess for what you think your function looks like. In our case of applying this to a quantum chemistry problem, it's going to be a guess of the ground state wave function. You're going to have a problem-specific cost function. In our case, that's going to be the expectation value of the Hamiltonian, so the average value of the energy, and we want to try to minimize that by varying parameters that are inside of our ansatz. Step 1 and step 2 are the part that are in principle done on a quantum computer. The training procedure, so minimizing the cost function, is what's going to be done, or what will be done in principle in a classical computer. We're not going to use a quantum computer today simply because we would just spend the whole morning waiting in line for a quantum computer to become available. So we're going to use a simulator to mimic that process. So, as I mentioned earlier, all of these variational algorithms are ultimately hybrid computations. So you're doing part of the work through the quantum circuit, through the quantum computer. You're doing part of the work, particularly the processing, on a classical computer. And then you have the two talk to one another, sharing data to some extent to achieve this ultimate goal of minimizing your cost function. And PennyLane was initially built very much with that kind of process in mind. It's grown a lot since then. It can do a lot of other things beyond variational circuits. But this is, to some extent, a general description of the short-term future of quantum computing. Even as quantum computers get better in the next 2-3 years, classical computers have had decades to be developed. Decades of algorithm development. They're very good at certain things. So likely for the next few years at least, you're going to see this hybrid computational model where part of the job will be done by a quantum computer, and increasingly bigger part of the job should be done on a quantum computer. And then the part, again, that the classical computer is good at will continue to be done on classical computers. So all that to say, quantum computers are not going to replace your laptops anytime soon. So this is the general setup for kind of a toy quantum chemistry problem that we're going to look at. I'd like to motivate PennyLane in that respect. So PennyLane is based on Python, if you've never used it. Maybe as a, I don't know if you can raise your hand or post something in the chat. How many of you have heard about PennyLane? Yeah, so you can raise your hands. Okay, perfect. Okay, for some of you, it's your first time. Okay, perfect. So over the next 4 or 5 slides, I'm going to give you a quick introduction to what PennyLane is, the general structure of a program, and then we're going to move on to the hands-on part where you're going to get to follow along in some coding with PennyLane. So PennyLane is an open source library based on Python. So if you've heard of Qiskit, it's somewhat like Qiskit. It's based on Python. It's meant for the programming of quantum computers. Both, I'd say it's both a simulator and to be able to use real quantum computers. Because it's Python, it tends to be relatively easy to learn compared to other languages. With it being open source, we have external contributors beyond Xanadu that have contributed to the development of the library. A big focus of PennyLane, at least initially, was to make everything differentiable. That continues to be true now. We try to make sure everything is differentiable. That becomes important, especially for quantum machine learning applications, where you constantly need to compute gradients or derivatives of things. And another important aspect of PennyLane is that it's modular. PennyLane tries to give you building blocks so that you can go off on your own and build applications from those building blocks rather than giving you static functions that are very difficult to generalize or that are very difficult to get into the details of those functions. We really try to equip users with modular units that they can put together in ways that even we at Xanadu may not have thought of. So in that sense, we really try to keep our users at the center of what we do within PennyLane, of the future of its development and the way that it's built. Again, we really try to put a big focus on giving building blocks so users have the flexibility in there to build different applications. If you've been on PennyLane.ai, you've seen that we have a lot of educational material, things like the codebook, the PennyLane demos, PennyLane challenges. We really try to make this accessible to as many people that are interested in learning quantum computing. And the differentiable quantum computations, this is going to be important for us today because we're going to need to calculate gradients in our training procedure. And PennyLane natively supports those types of computations very nicely. So in that sense, PennyLane has been built for various applications. You have things like automatic differentiation of circuits, which you can think of as a better way of computing derivatives and gradients beyond finite differences or beyond what you may be used to from your early studies. It accommodates very nicely hybrid and classical models. So this interaction between the quantum computation and the classical computation. But it also lets you interface directly with both different frameworks and different hardware. So it has a device independence that makes it natively support hardware beyond that developed by Xanadu. So I mentioned PennyLane can act both as a simulator and a way to connect to hardware. We have a range of different simulators within PennyLane. The one we're going to use today is this default.qubit simulator. This is it's a powerful but basic simulator that will get you to about 12 qubits or so, being able to simulate that on your laptop. If you want to look at things like noise, how noise starts to affect your computation, we have a simulator for that called default.mixed. And once you start gaining more experience in quantum computing and you want to try out problems that require a larger number of qubits or more resources, the Lightning devices that are listed here at the bottom are really meant for that, for those advanced use cases where you need more resources, more computational resources. So what these Lightning devices are, they're essentially high-performance C++ simulators. So they're still native in Python, but they have a C++ backend to do the heavy lifting behind certain computations. On your laptop, you can already use this Lightning.qubit simulator. This will help you once, it depends on the problem you're doing, but probably once you get past 10 qubits, the Lightning simulator will be useful to you. We also have simulators that support GPU hardware. So if you have access to GPUs somehow, whether on your machine or within your university or institution, then the Lightning GPU and Lightning co-host devices are something that you can explore down the line as well. Now, I mentioned that there's this device-independent feature of PennyLane. We're very proud of this feature. PennyLane can be used to connect not just to Xanadu hardware. In fact, we actually don't really recommend using PennyLane for Xanadu's current hardware that's available on the cloud. Instead, we've created plugins that if a user has an account with some of these other hardware providers, so IBM, IonQ, AWS Bracket, you can interface with our hardware using PennyLane. Again, it doesn't provide a backdoor to the hardware. You still need to have an account, and you still need to abide by whatever access model that company has. So currently for IBM, if you have a free account, you're limited to the 10 minutes of computing time a month. If you're on something like AWS, you have this pay-as-you-go business model that to be able to access their hardware, you need to pay for it as you use it. But the nice thing is that you don't need to learn the language of each of these hardware providers. You can really interface with their hardware directly with PennyLane by effectively changing a single line in your PennyLane code. It also interfaces nicely with other simulators, so Google simulators, NVIDIA simulators. It interfaces very well with other popular, particularly machine learning frameworks that have been developed. So things like TensorFlow, PyTorch, and JAX integrate very well with Python, with PennyLane. We won't see very much of that today, but if you explore the PennyLane demos, you'll see applications, especially to JAX and PyTorch, of how they can be used in conjunction with PennyLane. So just to refresh your memory or to put everyone at the same level, if you're relatively new to quantum computing, quantum computations are described abstractly in terms of quantum circuits. The way that you read a quantum circuit is you always start from some basic initial state, typically all of your qubits in the 0 state. You perform certain transformations on those qubits. That's how you're doing the computation. Those transformations are described by different gates. I show a subset of them here. You can have gates acting on just a single qubit, gates acting on multiple qubits at the same time. Some of those gates are going to depend on parameters. That's going to be important for us today because we're going to have parameters that we're going to vary within the gates. And importantly, something that is very useful to keep in mind is in quantum computing, all your circuits have to end in a measurement process. If you don't measure what your circuit has done, you're not gaining any information out of your computation. So you always need to do this measurement. Remember, measurements in quantum mechanics are probabilistic. So in practice, you need to perform several measurements to get a good description of your system. You're going to get a statistical average of the description. So sometimes your computation is going to give you a slightly wrong answer. Sometimes it's going to give you the right answer. And really what you're trying to do with a quantum algorithm is increase the chances that you get the right answer as much as possible. You want to minimize the chances of probabilistically getting the wrong answer and maximize the chances of getting the correct answer that you're after. So what we're going to see is within PennyLane, these quantum circuits are going to be represented by Python functions. As you know, the order of operations along the horizontal axis, you can think of that as the direction of time. So in this case, you first apply this gate, it's called a CNOT gate, and then you apply a Hadamard gate, and then you apply the Foley gate, and then another control rotation gate, and so on. So the order in which the gates appear is the order in which they appear in a PennyLane program, is the order in which they act on your qubits. And then finally, I mentioned that any quantum circuit has to end in a measurement, at least a partial measurement of some of your qubits. this is what we're going to return in our Python function. So you can think of it as what's being read out of the quantum computation is what your Python function is going to be returning. That can be things like probabilities. It can be expectation values, different kinds of observables that you might be interested in. Finally, something that's a little unique to PennyLane is the idea of a Q node. This is sometimes a point of confusion, so I want to take a little bit of time to explain what Q nodes are. I mentioned that in PennyLane we have devices. The devices can be either simulators, so things like default qubit or the Lightning devices. It can also be real hardware. Your device can be an IBM quantum computer, an IonQ quantum computer. You have your description of your quantum circuit as a Python function in PennyLane. And what you need is a way to connect your description of your circuit to the device that you're using. And that's what a Q node does in PennyLane. A Q node is used to connect the device that you're using to the computation that you want to perform. So effectively, all quantum computations in your program are done within a Q node. The Q node is what interfaces with the classical world. So it's what's going to take inputs into your quantum computation. So things like data, if you're looking at a quantum machine learning application, things like parameters that your gates will depend on. And it's also what you're going to, it's also what's going to feed the information out of your system. So once you perform a measurement, you're getting classical information out of your computation. This is external to the Q node. So the way that a typical PennyLane program looks like, this is a simple one. But I want you to take a minute to kind of take a screenshot of sorts with your mind, because we're going to see this in the example we're going to do. So typically, you first define the device that you want to use, whether it's a simulator or a hardware. You then have a Python function describing your quantum circuit. There's a couple of ways of defining a Q node or of using a Q node to link that Python function to your device. The one we're going to use is the format that's shown here. So we're going to be decorating our Python function with this Q node that says, I want you to run this circuit on the device that I defined above over here within this Q node. At the bottom here, we're also going to see that today we have classical processing of part of the computation that will be external to our Q node. As you can see, the Q node is only what's immediately below that line. This cost function, for example, would be a classical computation that if we were to be doing the circuit in a real quantum computer, the cost function would be calculated in a classical one. And same thing with the gradient over here. And one of the strengths of PennyLane is the easy integration of both this quantum computation and classical computation outside of the Q node. All right. Any questions here before we move to the example? So what we're going to do is I'm going to give you a quick description of the algorithm, of some of the details of the VQA algorithm, and then we'll jump into the example. We're here. In principle, yes, X and Y can be an array. PennyLane this computation supports broadcasting in PennyLane. So if you were to do a cost function with x and y being arrays, you're going to get an array of cost functions rather than a single value. Okay, so remember, we're going to run this V2E algorithm. We're going to see that we're going to prepare a Hartree-Fock state. That's done under the hood, essentially, in PennyLane. We've done the computations for you, and we just need to call a certain function in PennyLane to do that. We're going to create a post-Hartree-Fock state. We're going to do it in a bit of a special way using something called Givens rotations. And then we're going to optimize the parameters of that circuit or optimize the parameters of these Givens rotations to minimize the expectation value and then try to get a good estimate for the ground state energy. So, the Hartree-Fock state that we're going to start off with, that would in practice be done by a classical computation. They've already been designed to be very good at that. We're going to feed that into our quantum circuit. And then the job of the quantum computer will be to improve on that ansatz. We want a better description of the Hartree-Fock method. We know that Hartree-Fock is limited in what it can do. We want to try to do something better than that. And we're going to do that through a series of gates that are described here in this cartoon by these G's. These are these Givens rotations that I'll describe in the next couple of slides. And then we want to extract a new estimate for the energy out of this new post-Hartree-Fock ansatz. So most of you, if you've done quantum chemistry, you're familiar with the description of the Hamiltonian and the wave function in terms of kind of position of the electrons, Coulomb interactions, kinetic energy. That description is not really amenable to quantum computers. We need a way to represent those molecules and those Hamiltonians using qubits, because that's what we're using as the computation. That's our basic unit of computation. So the way we can describe molecular wave functions in terms of qubits is a sort of occupation number representation. When you have a molecule, you have orbitals that can be occupied by electrons. Those orbitals are going, or those electrons can be represented as qubits. So our Hartree-Fock state, for example, and this occupation number representation is the lowest possible occupation of your orbits. Each orbit can take up most, in this case, you can think of it as 2 qubits. One of them in this cartoon pointing up, the other one pointing down. You can't ever have 2 qubits pointing in the same direction within a given orbital. So once you've filled up an orbital, you need to move on to the next one. The Hartree-Fock one is occupying the lowest possible orbitals up until you run out of qubits, or you run out of electrons in your molecule. If you want to describe something beyond the Hartree-Fock state, you are now occupying a different set of orbitals, or you're occupying higher orbitals that may not have an electron associated to them in the Hartree-Fock approximation. So what we're going to see then is we have a reference state, or Hartree-Fock state. We're going to do this for the hydrogen molecule. So we're going to have 2 electrons. That means that the lowest orbital is going to be fully occupied. The other orbitals are going to be free. We need a way of describing different ansatz. And the way that those will come up will be the higher orbitals are occupied in some way. We're going to have single excitation gates that will take us from a reference state to one of the electrons being in a higher orbital. And we can have double excitation gates where now relative to a reference state, where it's going to differ by two electrons being in different orbitals. So that can be the one that's down is now in the second orbital, the one that's up is now in the first orbital, and the 0th orbital is now empty, for example. And we're going to construct essentially a mixture of these single and double excitations to improve on the ansatz. So the way that the single excitation gate is described, or one of the ways that is described, is you need something known as a particle conserving gate. You have some restrictions when you modify your reference state. Whatever operation you apply, you can't let it get rid of an electron. You're only trying to excite it to a higher orbital. If you get rid of it, then you're not preserving the number of particles, and you're effectively changing the problem that you're trying to solve. So it's very important that whatever operation you apply, that it preserves the number of particles in your system. One way of doing that is with this Givens rotation, which forms, or controlled Givens rotations form a universal set of operations within quantum chemistry. Don't worry too much about this matrix description. This is just, if you're curious about what this Givens rotation looks like mathematically, this is what it looks like. But what I want you to keep in mind is this qualitative picture of exciting one of the electrons in your orbitals to a higher orbital. That's what a single excitation gate will do. In contrast, the double excitation gate will do that twice to some extent. So now if you start from your reference state where your lowest orbital is fully occupied, the double excitation gate will take both of those electrons to the second orbital if you're limited to 2 orbitals. Again, you have the mathematical description here. It's not super important for today's purposes. Really just try to keep this qualitative picture in mind. So we have a way of describing effectively our wave function in terms of qubits. We also need a way of encoding the Hamiltonian in terms of qubits, or in terms of the most popular kinds of operations that exist in quantum computing, which are poly operations, poly gates. I won't go into the details, but effectively from the Hamiltonian that you're used to, that has the Coulomb interaction, the kinetic energy, you transform that into what's known as a second quantization form, where you're now encoding the anti-symmetry property of electrons within these A operators. There's a certain mapping that will let you go from these operators, from this description over here, the second quantized description, to a combination of poly operations, which can be very effectively done in quantum computers. So if you can describe everything in terms of poly operations, you're able to do that computation in principle on a quantum computer. You know how to build a circuit for that. If you've ever tried to do this by hand, even for the hydrogen molecule, you know that it's extremely tedious, both because it tends to be a lot of repetition and because it's a very long computation to do. The nice thing is that PennyLane will do all of these things that I just described to you, these single excitation gates, building the Hartree-Fock state, describing the Hamiltonian in terms of poly operations. It will do all of that in a very simple way for you. And that's exactly what we're going to do now. So we've arrived at the hands-on portion of the talk. So I believe Xanadu shared instructions on how to get started. If you haven't had a chance to follow the instructions, what I recommend you do is that you search Google Colab. If you search Google Colab, you'll get something like this, and then you can click on New Notebook This is really the fastest way to get started. If you haven't installed it locally in your machine, Google Colab will work just fine for our purposes today. So I'll give you a little bit of time to open up your Google Colab session. If you can just comment on the chat once you're ready, that'll give me an idea of when to keep going. Okay. Some responses are starting to come in. I'll wait a little bit longer just to make sure everyone is online. Okay, yeah, QRate should work as well. Okay, so I'm going to use this version. Don't worry about the comments. This is more to guide you as we go through it. So if this is your first time running PennyLane in the notebook that you have opened, what we're going to start off with is installing PennyLane in the servers that we've connected into Google servers effectively. So I want you to type this ! pip install PennyLane. You can either click on the play sign, or if you're on a PC, Control Enter. If you're on a Mac, Command Enter, and it should run the cell for you. This might take a few minutes. If you're in a brand new codebook and you've never used one before, it's no different. You just do pip install PennyLane. Just give it a second to run. Okay. And then if you want to have a new code cell, you can either click at the top left here with this plus code, or if you go to the bottom of your existing cell, you'll also get a prompt for adding an extra code cell so that you can keep going. If you want, you can generate a few of these. We're going to need a few code cells. Once you've installed PennyLane, we are going to import PennyLane and a couple of other libraries within, or modules within PennyLane. So for historical reasons, we import PennyLane in shorthand as QML. Within PennyLane, we're going to need a special version of NumPy that we're going to call in shorthand PNP, short for PennyLane NumPy or NumPy. And then we're also going to need the QChem module for some of the things we're going to do today. So once you type out these 3 lines, you can run that cell. Zoom in. Okay, so to start, we first need to define the molecule that we're interested in studying. To keep it simple, we're going to stick to the hydrogen molecule. So we're first going to describe a variable called symbols. And we're going to specify the symbols of the atoms that make up this molecule. In this case, it's 2 hydrogen atoms. We also need to describe the coordinates of the hydrogen atoms, so where they're found in a given coordinate system. We'll do that by defining this coordinates as an array.
I'm heavy this is important. I'll keep something. Go up my Instagram too.
Okay. So we need to describe where each of these atoms are. We're going to assume that they are, if you think of a typical coordinate system with X, Y, and Z axes, we're going to say that both of the atoms are along the Z axis, equidistant from an origin. The distance that each of them is found from the origin, we're going to take as minus 0.6614 and plus 0.6614. These numbers, you can find them online. There's databases for different molecules that people have studied. I've already looked that up for you, so you can just copy these numbers for now. Okay, this is the equilibrium distance in standard units, in so-called standard units, between the hydrogen atoms in a hydrogen molecule. So we can, I think I missed something here. Yes. Missed that other square bracket. Okay, so we've defined the molecule we're interested in. Now we're going to build the molecular Hamiltonian. This is that part of where we're taking the Hamiltonian that you're used to seeing in terms of kinetic energy and Coulomb potential in second quantized form, and then in terms of a series of polygates or polymatrices. So the way we're going to do that is use the QChem module in PennyLane. It has a built-in molecular Hamiltonian function that's going to output our Hamiltonian as well as the number of qubits that we need to describe our molecule. As inputs, we need to give it the description of our molecule. So we need to give it the symbols that we've defined, as well as the coordinates of where the atoms in this molecule are. And just to make sure that we've done this correctly, I'm going to add a couple of print statements. Okay, so I'm going to print out the number of qubits that PennyLane estimates we're going to need, or computes that we're going to need for this molecule. And we're also going to print out our qubit Hamiltonian. Okay, so if you did this correctly, you should see that we're going to need 4 qubits to describe the hydrogen molecule. The qubit Hamiltonian, you should see the series of symbols. So the numbers are, if we go back here, you can think of the numbers as these HPQ and HPQRS, so they're coefficients. And you can see some of the poly operations here. So you have an identity acting on your first qubit, a poly Z operation acting on your 0th qubit, another poly Z operation, but this time on your second qubit, and so on. Okay, this, if you go all the way through it, you should see about 15 terms to describe just the Hamiltonian for the hydrogen molecule. So you can see already that even for the simplest molecule, a hydrogen molecule, the qubit Hamiltonian gets very complicated. And the nice thing with PennyLane is that it's able to do these kinds of computations for you very simply, just by calling this molecular Hamiltonian function. Okay, so next we're going to create our Hartree-Fock initial state. To do that, we need to specify how many electrons exist in our atom or in our molecule. And then to build our Hartree-Fock state, we also have a built-in function called HF state, which takes as input the number of electrons in our molecule, as well as the number of qubits that we need to describe our molecule. And then we can get an idea of what this looks like. And you should get confirmation of what I mentioned earlier. Remember, if we have 4 qubits, we have 4 possible states. I said that the Hartree-Fock state is, in this occupation number representation, you're occupying the lowest possible ones. And you can see that here, we've occupied the 2 lowest orbitals and the other 2 are free. The other 2 positions are free. So if you're getting this error, qubits is not defined, remember molecular Hamiltonian outputs 2 variables. One of them is your Hamiltonian, the other one is the number of qubits. Okay, so we've done the initial steps of our computation we've mapped the Hamiltonian in terms of qubits. We've built our Hartree-Fock state. Now we want to define the circuit that is going to prepare this post-Hartree-Fock ansatz. So it's going to build up on the Hartree-Fock state that we built into something hopefully more accurate. So we're going to define our circuit here. It's going to depend on certain parameters, which we'll call param. And it's going to take a certain number of qubits. In PennyLane, we typically call qubits wires because they're often represented just by horizontal lines. There's other reasons that are more complicated than that, but just take it to be because they're represented by horizontal lines that look like wires. So the first thing we need to do is encode this Hartree-Fock state into a quantum circuit. Remember, a quantum circuit starts with everything, all the qubits in the 0 state. We want to tell the circuit, I want you to encode this Hartree-Fock state that I built classically into the circuit. The way we do that is with this basis state function, where we feed it the state that we want. In this case, we have called that HF. And we want to use all of the qubits in our circuit. So we say, apply or build this basis state by using all of the qubits in our circuit. Then for the hydrogen molecule, there's different types of ansatz that we can try. Because I've done this problem before, I can tell you that it's going to be enough just to have a single excitation, a solitary double excitation gate. So just one double excitation gate. That's going to depend on this parameter that we're going to feed into the circuit. And this is going to act on all of our qubits. So remember, a single excitation gate links it links 2 qubits, so it operates on 2 qubits. A double excitation gate will act on 4. So we need to span all 4 of the qubits in our circuit. Okay, so we can run this cell. We've just defined the circuit that we're going to run later on in our Q node. So this is where we start building up the quantum computation. We need to define a device. So in this case, the simulator that we want to use. We need to create a Q node that's going to link the device to we haven't defined an output to the circuit yet, but whatever the circuit computes plus an output or an observable. So to define a device, we're going to call that def qml.device. For today, it's going to be enough just to use the default .qubit simulator. And whenever you build a device, you need to tell it how many qubits are going to be in that device. Again, the variable within PennyLane for qubits is called wires. This qubits here is the number of qubits that are molecular Hamiltonian function computed for us. So if everyone is following, we can now build our Q node. We want to run the circuit that we defined above and this default.qubit device that we just created. We're going to define our cost function, which is what we're trying to minimize. That is going to take the parameter for double excitation gate. It's going to run the circuit that we defined above across all of the qubits, so across the entire range of qubits that we have. And then because we're interested in the expectation value of our Hamiltonian, what we're going to return is exactly that. We're going to return the expectation value of our Hamiltonian. So there's our cost function. We have an ansatz that starts off by being the Hartree-Fock state. We improve on that. We build a post-Hartree-Fock state with this double excitation gate that's going to depend on some parameter. And then we're going to output the expectation value of the resulting or the resulting expectation value of the Hamiltonian. We can get an idea of what our circuit looks like by using this draw MPL function. We need to tell it what circuit to draw. And we're going to give it just a random value for param. So externally to these parentheses, we need to specify the variables that will go into that circuit. And if everything has worked well, you can see a pictorial representation of the circuit that we just built. So to confirm, we have 4 qubits describing our hydrogen molecule. This first gate is describing the creation of our Hartree-Fock state. So it would be this line over here, this QML.basis state. And that's this first gate. Our double excitation gate is represented over here. If you want to get if you want to be able to see the parameters of that gate, you can also add a variable called decimals. Then you can see here, you can also see what the parameter of your double excitation gate is. All right. Again, if you have questions, if I'm going too quickly through this, just let me know on the chat. So for everyone that's following, as confirmation, you should be able to get this circuit. after everything that we've done. So this X file, remember your quantum circuit has to return some kind of observable, some kind of classical value. What we're returning here is the expectation value of the Hamiltonian, which is, we go back all the way here. We're returning this. The expectation value for Hamiltonian is an estimate of the ground state energy. The ansatz that we built is an approximate description of the ground state. If you take the expectation value of the Hamiltonian with respect to that ansatz, you get an estimate for the ground state energy. So that's why we're returning X val, because this is what we're interested in getting. Does that make sense? Why we're returning X val H? Yeah, okay. Yeah, at the moment the slides aren't shared. I can share them with Sienna afterwards, and then she can share them with everyone afterwards. But yeah, the slides currently aren't public, which is why you can't access them at the moment. So let me go back here for the question in the chat. So remember, the Hamiltonian is an operator that's associated with the observable of energy in a system. If you want to get the value of that observable from its operator, from the Hamiltonian, you need to calculate the average value of the Hamiltonian, so to speak. So the value of the energy is the expectation value of the Hamiltonian. So yes, our cost function is this E alpha, which we're trying to minimize. The way we compute that E alpha is as the expectation value of the Hamiltonian. So they're the same thing.
Yes, yeah, thank you.
Yeah. So yeah, our purpose now, or purpose of the classical processing that we're about to do, is going to be to minimize X val H.
Yes, usually in machine learning type of situation, we just compare this E of alpha with the reference value, and then we try to minimize the difference. So that's why I got this term.
Okay, I see. Yeah, you can define different cost functions.
Yeah, sure. Thank you.
Yeah. Let's go back here. So now we've done, in principle, what would be done on a quantum computer. We're going to do the classical computation now. So we're going to first choose an optimizer. For those of you that are done machine learning, you know that there's a whole zoo of optimizers that you can choose from. For today, we're just going to do a very basic gradient descent optimizer. So admittedly, not the best type of optimizer, but it'll be mostly good enough for today. Yeah, I'll also share the notebook with Sienna, and then she can distribute it afterwards as well. So you're gonna, if you miss anything right now, you're going to have access to it afterwards. So within this gradient descent optimizer, same thing for the slides. I'll share them afterwards so you can get access to them. Within the gradient descent optimizer, we're also free to choose a step size. There's a default step size within this function in PennyLane. We're going to change that to a different one. Typically, the step size is a parameter that you vary as well. You modify it to improve your optimization. For today, we're not going to do that. We're just going to choose a static step size and just run with that one. We are going to also, we need an initial guess for our parameter. Our parameter is a rotation angle, so we're going to call that theta. And we're going to give it, you can give it any value you want. I'm going to choose 2. And what we're about to do, we need to be able to differentiate Python arrays or NumPy arrays. Typically, NumPy arrays are not differentiable, which is why PennyLane has its own special version of NumPy. To make the array differentiable, we add this option that says requires grad true. Okay. So now now that we've set up our optimization, we're going to iterate through it. We're going to take a step in the optimization, recompute the cost, evaluate the cost function. If it's still not low enough for what we want, we'll do another iteration and so on. So we are going to want to store the value of our cost function, which in this case is the energy we're trying to estimate. So for now, that's just going to be the value of the cost function at the value of theta that we randomly defined. Again, you can take any other value that you want. It doesn't have to be 2. We also want to store all of the values of our parameter that we find. At the moment, it's just one, the one that we call theta. Typically, when you do these types of optimizations, you have 2 choices. You can either limit yourself to a maximum number of iterations. So you can say, I want to run the optimization loop 100 times. It doesn't matter what happens at the end of those 100, I'll take that answer. You can also define a convergence tolerance that says, if between one iteration and the next, my value doesn't change by more than what I set as a tolerance value, I can stop the optimization. We're going to do both. So it's good practice to set a limit to the number of iterations so that you don't get stuck running an infinite loop or a very long loop, an unexpectedly long loop. We're also going to define a convergence tolerance. So for today, we're going to say if the value of the cost function or the value of the energy doesn't change by more than 1 times 10 to the minus 6 or 1/1,000,000th by less than 1,000,000th, we're going to stop the optimization even if we haven't reached the 40 iterations that we set as an upper limit. So now we're going to repeat this optimization process by running it through a for loop. I'm going to run it at most for the maximum number of iterations that we defined above. At each step, we're going to compute the new value of our parameter, so a new value for theta. And we're also going to store, we also want the previous value of our energy. These are going to be the outputs of our optimization after taking a step and recomputing the cost function. As input, we need to give it the cost function itself, and we need to give it the current value of the parameter. Once we have that, we're going to store the new value of our cost function for the new parameter that we've outputted, and the new value of our parameter. Okay, so this theta that's coming out now is going to be different than 2. And we want to store what that new value is. We're also going to estimate the convergence as the previous value or the current value of the energy minus the previous value of the energy. Yes, theta in this case is related to the 0.2. So in general, this is theta. At the moment, we've chosen that value to be 0.2 in the drawing. Here, we chose it to be 2. Now that's going to change as we go through the optimization. Yeah, no one. So we calculate a convergence if, let's say, every 2 iterations, we just want to make sure that things are going well. So we're going to compute, we're going to display the step size that we are at and our new estimate for the energy. I wanted to 8 decimal places. Oops. PennyLane, by the way, by default, uses energy in terms of hard trees. So these are standardized units in atomic and molecular physics. And then finally, if before we finish the total number of iterations, if we've satisfied our convergence tolerance, so if the convergence that we calculated here is smaller than the tolerance that we defined above, we're going to break out of our for loop prematurely, possibly. And so we can run this, and if done everything well, which I haven't, I didn't run these ones. Okay, you can see we start off with pretty high energy. We start off at about minus 0.4 hard trees. As we go through our optimization, you can see that the value is getting smaller. It's getting more negative, so it's getting smaller. And then we start to converge somewhere around minus 1.13 hard trees plus some decimal values. If you want to get an idea of what this looks like, don't worry about copying all of this code. Again, this notebook will be shared with you afterwards. Oops. Change things. So for the case of the hydrogen molecule, we know very well what the proper ground state energy is. That red line over here, this EFCI, FCI for full configuration interaction, is the energy that we're aiming for. The green line here is our estimate from our post-Hartree fog ansatz. You can see that we start off pretty far off from the true value, but as we optimize the parameters, we get closer and closer until we reach the convergence that we define. Remember, any computation, whether classical or quantum mechanical, always has to satisfy a certain accuracy that typically you set depending on the application that you're looking for. Okay, so the important thing here is if you're able to get somewhere close to minus 1.13, then you've done the optimization correctly for H2. One thing that I want to mention quickly, and it's something that it's based on some recent work we did at Xanadu, is the state that you start off with, your initial state, can make a big difference in your computation. So I mentioned that most things in quantum chemistry start with a Hartree-Fock state. There's ways of classically going beyond the Hartree-Fock. So there's classical post-Hartree-Fock computations that you can do that you can then encode into your circuit. If you do that, if you start from a state different from the Hartree-Fock state and then apply different ansatz within your circuit, it will sometimes improve the performance of your workflow. We won't go into the details here, but just to give you an idea, there's two other post-Hartree-Fock methods that I'll just call CISD and CCSD that try to account for some of the correlations between the electrons in even the hydrogen molecules. So the Hartree-Fock state neglects them completely. These two methods account for the correlation between them a little bit more. What you can see here, I should mention, however, both the CISD and the CCSD methods start from the Hartree-Fock state and then just modify it a little bit further. What you see here is that same routine that we just run, that same VQE routine that we run. The red line showing the Hartree-Fock state, the blue and sort of aquamarine line that falls on top of the blue line represents the computation using these other classical post-Hartree-Fock states. You can see that it converges a lot faster. It converges after less than 10 iterations, whereas the one that started from the Hartree-Fock state requires about 20 iterations to converge. And you already start off from a better value. So sometimes it's not a matter of building just a better ansatz in your quantum circuit. It might even be taking the little bit of extra time that it would be to build a better classical ansatz and then going into the quantum computation. So the main difference between PennyLane NumPy and basic NumPy is this differentiability of the arrays. With normal NumPy, the arrays are not differentiable. PennyLane NumPy arrays are differentiable, so it lets us compute the gradients that we did. Yeah, so I'll share the note. When you get the notebook, you're going to get the code that generates this graph. In this case, to do CISD and CCSD, we are using PySCF. So this one. should be data sets. So within PennyLane, we're interested in reducing the time to research that users have. You don't always want to have to go through that pipeline that we just went through of building the Hamiltonian, building the Hartree-Fock state, finding VQE parameters. We've made a set of a series of data sets available for different molecules, for different spin systems, for certain quantum machine learning applications, so that you can get started faster in applying your getting applications off the ground rather than having to recompute parameters in your ansatz, recompute Hamiltonians. It's all ready to use within these data sets. You can see some examples of different molecules that we have data sets available for. You have pretty large molecules like this C2H6. This is, if you go into the data sets page within PennyLane, you'll see something like this. You can choose different configurations, the different bases that you want to use, different bond lengths. Each of these typically have a Hamiltonian associated to them, a estimate of the VQE energy, estimates of the given rotations parameters for different ansatz and so on. So it's really with the hope of helping you get started faster in applying these things. You don't have to recompute basic quantities all the time. You can start off from pre-computed quantities and use that for an application of interest. You can see here some ideas. You have bases, you have the spectrum, the dipole operation, the Hamiltonian, the Hartree-Fock state for a whole range of different molecules. And in the notebook that I'll share with you, you're going to get the code as an example of looking at the H2 molecule or looking at the H3 molecule, one of those two. So I want to wrap up. I know it's been almost 2 hours that you're in need of a break. Just kind of closing off the purpose of the talk and why there's so much interest in looking for applications of quantum computing to problems in quantum chemistry. The hope is that we will be able to compute things like ground state energies, excited state energies, reaction rates more accurately or more efficiently than is currently possible, especially for very complicated systems. Of course, there's a whole range of libraries. I mentioned one of them, this PySCF library that can be used in conjunction with PennyLane to compute other quantities beyond some of the ones listed here. Within Xanadu, we're very interested in applications to estimating or computing the properties of materials, particular materials that can be used to improve the design of batteries. So improve the charge time of batteries. Here in Canada, for example, because it gets fairly cold in the winter, it's very difficult for batteries to maintain their charge in that cold. So the charge drains from the batteries when it gets too cold outside. And it can make electric vehicles very unreliable in countries like Canada. So we're looking for ways to help experimentalists design better batteries through computation. We've also largely moved away from variational algorithms. So the VQE is a very nice example at an introductory level. It's easy to understand, it's easy to apply, but at this point, it seems unlikely that it'll offer any kind of computational advantage over classical methods. One algorithm that is fairly expensive in terms of number of qubits that it needs, but that is a good candidate for this type of application is the quantum phase estimation algorithm that the circuit is depicted here. It's not important for today, but just to show you that there's algorithms beyond variational circuits that there's a lot of interest in for when the hardware, for when we have good quality logical qubits and a large number of them with her quantum computers ready to go. So if nothing else, there's a couple of things I want you to take away from this talk. One of them is, for a given problem, it's important to use the right tool. I mentioned that quantum computations won't solve every problem. It won't make every problem faster. You really have to find where things like quantum computing, where things like even using GPUs versus CPUs is advantageous. It's not for all the problems that you'll encounter that you'll always need, bigger tools, better tools. And the other thing is, of course, it's related to that, is that quantum computing isn't always faster or better. Okay, it's not that, if you try to estimate the ground state energy of a hydrogen molecule with a quantum computer, you probably won't do better than the classical methods. It's really when you start getting to complex molecules with certain characteristics that you might start to see an advantage. If you're interested in learning more about PennyLane, I encourage you to check out the website, PennyLane.ai. Join the community. So we are very invested in the community. We're on social media. We have a discussion forum where you can ask technical questions about PennyLane or about quantum computing. We monitor that very closely, so we'll be happy to answer the questions that you have for us. We also have a newsletter. If you scan this QR code, you can subscribe to our newsletter as a way of keeping up to date with what we're doing, with what demos we've released, the new demos we've released, new releases of PennyLane, new things that we're doing at Xanadu. You can also reach out to me directly if you have questions. I, of course, have limited power within the company. I can't help you get a job at Xanadu, but I may be able to offer some advice on things that you can try. And with that, thank you for your attention. I know we started off a little bit early in the morning for a lot of you. I appreciate you taking the time and staying for the duration of the talk. What is the potential experiment to do in PennyLane for communication? I'm not sure I understand the question. What do you mean by communication? I see. For quantum communication, I will say the number of features that we have in PennyLane for things like quantum communication is limited. We may release some material, for example, on the BB84 protocol, if you're interested in that. There's ways of simulating that in PennyLane as well. From what I remember, I think ethanol is probably the limit of what you can simulate classically, or what you can mimic classically. Once we get to real quantum computers, it'll be possible to do those types of computations. But right now, if you just try it on your laptop, you'll probably run out of memory if you try to do ethanol or methanol. And yeah, as Yana said, the recording will be available on the QCenter YouTube channel. I'll also share the slides and the notebook so that can be distributed to everyone as well.
Sorry to interrupt. So I sent you the link to the questionnaires, and if you participate in it, I can get your emails and I can send you the code and what was it? The slides. If
Yeah,
you
the slides.
send us the email address.
Yeah. So for the BB84 one, it's not online yet. There might be soon. We just have to see when we can fit it in. I would say probably transition. If you're talking about transition metals like molecules, it's probably complicated. Yeah, you may not be able to simulate them classically, but yeah. Yeah, thanks everyone. I hope you have a good rest of your day.
Thank you, Danielle.
Thank you, Sienna. Thanks for organizing this.